So apparently this example just asks us to multiplying things, so this should not be hard. So let's see, my A is 3315. I want to multiply this by 3 and negative 1. So let's see what we will get. Let's see, 3 times 3 minus 3 times 3 minus 3, so that's a 6. And then 3 minus 5, so that's going to be negative 2, so I get 6, negative 2 here. Okay, so far so good. My A is 3315, and then my 1. So that would just be 3 times 1 plus 3 times 1, that would be a 6. And then 1 times 1 plus 5 times 1, that would be another 6. Okay. By the way, in case you don't remember, we actually did this in the last lecture. This is actually the number from example 9.1. In example 9.1, we actually also see that this 6 and negative 2, this is actually just 3. This is actually just 2 times 3 and negative 1. So that means 3 and negative 1, this is my eigenvector corresponding to the eigenvalue 2. And also this 6, this is just 6 times the vector 1. So my vector 1, this is the eigenvector corresponding to the eigenvalue of 6. Okay, so far so good. Nothing new. Now I want to multiply A to 3 and negative 1 and 1 and 1. Notice that this guy is actually just the two vectors that we see earlier put next to each other, 3 and negative 1 and 1 and 1. Well, let me just play along and multiply this guy out. So that would just be 3 and then 1 5. And then I will have 3 negative 1 and 1 and 1. So what I'm gonna get? Let's see, I'm gonna have 9 minus 3, so that's a 6. 3 minus 5, so that's a negative 2. I have a 3 plus 3, and that's a 6. I have a 1 plus 5, which is a 6. So notice that the product is actually just the two. Okay, let's see, what color should I use? Let's see. The product here is actually just the two products that we have earlier put next to each other. Oh, so now I realize how my coloring is just off. Okay, this is my eigenvector. This is my eigenvector. This is my eigenvector being put next to each other. Okay, now I guess this makes a little more sense. This guy is just this guy, and this guy is just this guy. And then, so that's my eigenvector. Okay, so it seems like if I multiply my matrix A with the two eigenvector being put next to each other, the product, the actual product is gonna be just the original product here, 6 and negative 2, and here 6 and 6 being put next to each other. And let's see how does this fit into the big picture. I have here the same matrix A. Wait a minute, this is not the matrix A. This is the matrix that we have earlier. So this is the matrix of eigenvector. So this is 3, negative 1, and 1 and 1. So this is the same matrix that we kind of see up here. I multiply this by 2 and 6. Let's see what I'm gonna get. Let me actually kind of multiply it from here right away, because this is already brought in a matrix form. This is gonna give me a 6, and then another, another 6 here, and then negative 2 here, and then another 6 here. Voila! Notice how this two guys is actually the same thing. I have 6, 6, negative 2, 6. And that's what we also have back here. 6, 6, and negative 2, 6. So what really is going on here? Let's see. Let me actually call this matrix let me actually give this matrix a name. Let me call it P. So my P would be the matrix 3, -1, and 1, and 1. So this is the matrix where I actually just put all the eigenvector next to each other and just call it a matrix. I multiply P by the matrix A, which is what we do here, A times P. And the product would just be equal to this thing, which is P. So A times P, which is what we have here, equal to P times, and what is this guy? This guy is actually a diagonal matrix where the entry in the diagonal 2 and 6. Well, this is just the eigenvalues. So A times P is actually just the same as P times this matrix here, 2, 0, 0, 6. This is the matrix where the two eigenvalues, the two eigenvalues are in diagonal. So my rightmost matrix here, this is just the diagonal matrix where the two eigenvalues are in the diagonal. And my matrix P, once again, this is the two, just the two eigenvectors. So suppose now, let's say that I can find the inverse for P inverse. So if I can find the inverse for the matrix P, so actually let me call this guy a D. So I have here a P equal to PD. Let's say that the inverse for P exists. So suppose that I can find P inverse. If I multiply P inverse to the left of both sides of the equation, so I'm going to have P inverse times A times P equal P inverse times P times D. And this guy, well, P inverse and P, that will just cancel out because the product of the two would be just the identity matrix. I'm going to have P inverse times A times P. That is going to equal to this D matrix here. This is the diagonal matrix where things are in the diagonal, where the eigenvalues are in the diagonal. It turns out this is actually true in general as well. Let's say that my matrix A is a square n by n matrix and it has eigenvalues, these guys, lambda 1, lambda 2, and so on to lambda n. And they have eigenvectors v1, v2, and so on to vn. Then I can diagonalize the matrix A, and by diagonalize I mean I can multiply the matrix A at the front by P inverse and at the back by P, where my P will just be the collection of my eigenvectors. And that would be the diagonal matrix D, where the diagonal consists of the eigenvalues.